So today, what I'm going to talk about is some of the technical advances we've been making in the Harris lab towards taking our 1.5 millimeter membrane into the quantum regime. So here's a cartoon of the device I'm going to be discussing. It consists of a high finesse Fabry-Perot cavity, and at the center we've placed a silicon nitride membrane. It's about 50 nanometers thick. It's 1.5 millimeters on a side, and it's flexible, and so that acts as our mechanical element. So these things ring at a couple hundred kilohertz, and they ring for seconds. And they're partially reflective, and so they're coupled to the photons in the cavity through radiation pressure. And I'm not going to talk about this in too much detail, but I just wanted to highlight that this system is kind of neat in the sense that we basically have a giant shiny red knob, though it's kind of faded in this photograph over the years, with which we can tune between three fundamentally different Hamiltonian interaction terms. We can realize a linear optomechanical coupling, which is just standard interferometry. So the effective length of the cavity depends linearly on the position, so you measure x. We can realize a quadratic optomechanical coupling, where the effective cavity length depends on x squared. You can do cool things like QND and QND readout with this, though I'm not going to talk about that. And then we can also realize this funny thing where we've found a position to the fourth measurement. And we think we might be able to use that in the distant future to create Schrodinger cat states or something. But I'm not going to talk about these today. I'm just going to focus on what we've been doing with the linear optomechanical coupling regime. And it's going to just be a sort of informal status update on what we've been doing and what we've been thinking about while we try to laser cool to the ground state. So the first thing I'm going to show you is our semi-recent Homodyne results, where we've laser cooled doing a Homodyne measurement, and we got down to the tens of phonons level. And then I'm going to show you how we've implemented a new heterodyne measurement and some of the early results that we took within the last couple weeks, and what we're thinking about when we try to analyze this data. And then I'll show you some of the improvements that are on their way. So just to give you a brief introduction, and sorry again if I just fall asleep on this podium, if someone could kick it, that would be great. I'm pretty tired. Okay, so here's our system. We feed a laser in one end, and when it comes on resonance, light builds up inside the cavity, and then it leaks out either side. And we can measure the reflection or transmission, for example, with a photodiode. And that data is shown here. This is the transmission through the cavity as a function of detuning of the laser and displacement. And what you see is a series of different optical modes that oscillate sinusoidally as a function of displacement. And all that's happening here is you have the unperturbed longitudinal modes in the cavity. And when you put the membrane in, when it's at a node, there's not much electric field. It doesn't perturb the cavity mode much. It moves to an antinode. You get a maximal perturbation, and that gives you these sinusoids at half wavelength oscillations. What's cool about this plot is that I've just shown you that we can realize this funny quadratic optomechanical coupling and, of course, the linear. And what I'm going to do is just put the membrane here and focus on this for the rest of my talk. So again, you can do all kinds of neat things with this, such as squeezing and laser cooling. And when I started my postdoc in the Harris lab, that's exactly what they had just finished doing from room temperature. So they had a membrane in a room temperature cavity. They brought the laser closer to the sweet spot for optomechanical damping. And what they saw was the Brownian motion damped out. So sharp peak got smaller and smaller and wider. And from the area or the half width, you can tell that the temperature was down there at about 7 millikelvin. So the room temperature 7 millikelvin corresponds to about 45 million phonons on average, down to about 1,000. And this ratio, in the simplest case, doesn't depend on the starting temperature, so our thought was to start 1,000 times colder and get down to the quantum regime. And so that's what we started working on. Turns out it's pretty difficult to couple light into a cavity in a helium-3 refrigerator, if you haven't done it before, perhaps. Nonetheless, so it took about 2 years to get this to work, and it's working now, and this is the latest iteration. We basically, here's our helium-3 fridge, and we've bolted a breadboard to it. And then, well, it's a homemade breadboard. It's not something we just bought. And then we have a cavity bolted to that, and these are the two end mirrors that are clamped to it with these cylinders right there. And then on the inside of it, we have the membrane sitting on a motorized membrane mount that we can use to push it around and tilt it as we need, as we see fit. And then we couple in light using free space optics. We tried it with fibers originally. It just became really misaligned as soon as we cooled it down, and that would require more attocubes. It's also interesting to note that, or good to note, that this is a single-sided optical cavity, and the finesse is about 50,000 low temperature. So this whole thing goes into a vacuum can. It's about this big. and then it's put inside of our giant dewar. And then we have a bunch of optics that you can see up here on the top, whose job it is just to steer the beam around, shoot it down the tube, and then collect it at the top. And yeah.
Just out of curiosity, are you able to tune the cavity and see or is this RDND fixed?
Tune the cavity in what we can.
Like tilt one mirror.
Oh, we can't tilt one mirror, but we can aim the beam from the top, and then we can tilt the membrane so we can find this aligned state that we want. Yeah. So anyway, cold cavity. Okay, so the way that we characterize our system is pretty straightforward. And obviously I'm sweeping a few things under the rug here, but basically we fire our laser down into the cryostat, it interacts with the cavity, and then we collect the reflected light with a diode. Okay, and if we sweep the laser through the cavity resonance, what we'd see in the reflected amplitude is a dip, just due to losses or a little bit of transmission through the L or N mirror. And then we'd see a wiggle in the phase that looks something like this. And we can use either of these edges here to lock the laser to the cavity and compensate for vibrations and do feedback and these kinds of things. That feedback happens all at low frequencies, below 50 kilohertz, and our membrane vibrates at, well above 50 kilohertz. And so, as it does, these features are going to shake back and forth at the membrane's frequency, and we can just monitor the voltage fluctuations. And when we do that, we see exactly what we expect, which is a sharp peak at the mechanical frequency due to the membrane's Brownian motion at 400 millikelvin or so. Okay, I haven't really resolved this peak. It's very sharp, as you can see. If you want to measure the quality factor, it's easiest to just do a ring down. The way we do that is to drive the membrane to a large amplitude with a nearby piezo, unplug the drive, and then just watch as the amplitude rings down. That data is shown here. The only thing I want to draw your attention to is that on the x-axis here is seconds, so this is a 260 kilohertz object in our cryostat that rings for, 5 or 10 seconds, and the quality factor here is 5 million. And we've since measured 6 and 8 million, just depends on how we've thermally cycled our system. Okay, so that's great. We can also apply an independent cooling beam now at arbitrary detuning relative to the measurement beam we're using to lock as well. And when we do that, as expected, this sharp Brownian motion peak gets wider and flatter. So this is the Homodyne measurement. We're just monitoring the phase fluctuations from the membrane. And this is due to some technical issues that we've since corrected. We had to have the cooling beam at this funny detuning of minus 514 kilohertz. So we had to crank the power up kind of high. But nonetheless, we see this optical damping signal, and you can see it broaden out. And I've taken these peaks and plotted their shape as a function of cooling power over here. And what we see is basically what we expect to see. We see a frequency shift that's linear with power, and that's just the optical spring. That should be proportional to power. We see a linear increase in the half width, and that's just optical damping. Again, that should also be proportional to power. And we would expect the inverse area to increase linearly, and what we see is that it does initially, and then it starts to saturate. And we're not sure what the saturation is due to. It could be due to imperfect noise subtraction, background noise subtraction, or actually just heating from the noise on the laser at this high power. Nonetheless, we can estimate the temperature, get an initial estimate of the temperature by using the half width and this nice little ratio over here where the final temperature to initial is the ratio of the final Q to the initial. And if you plug in numbers, depending on where you want to decide that this curve is saturated, if you plug in this number, you get 10 phonons. If you plug in this number, you get 20 phonons. So we're in the tens of phonons level. So the point of this experiment was to see what we could do with our system with the simplest measurement. It's our displacement calibration using the areas agrees within about a factor of 3, and that's reasonable considering the various uncertainties in the different gain stages. But the point here is to demonstrate that to show good evidence that we're knocking on the quantum door with a pretty large, slow-moving object. And what we'd really want is a sort of bulletproof thermometer that starts to work well at these low temperatures. And this exists in the form of a thing called heterodyne thermometry. And so to see this, consider the amplitude of the light leaking out of the cavity as a function of frequency, and you'll see nothing. At 280 terahertz, you'll see a large peak due to the laser. That's just the laser frequency coming back at you. And then the membrane is phase modulating that, so you'll see sidebands due to that leaking out. And the thermometer lives in the sidebands, basically if you imagine that the membrane is in the ground state, light going in at this frequency from energy conservation can't be scattered up to this frequency, and so you'll get a sideband asymmetry that's proportional to these quantities here. So that tells you the average phonon number in the membrane, and that's what we're looking for. Okay? Up until this point, I've been showing you Homodyne measurement, which is to just land all of this on a diode. The diode is a square law detector, and so what happens is you get some indifference frequencies out, and these two sidebands are folded on top of each other, and that's the peak that I've been showing you so far. Okay? To do a heterodyne measurement, if you want to resolve both peaks, you just apply a very large, laser beam that's, in this case, 80 megahertz detuned. Its job is not to interact with the cavity at all. It just bounces off the cavity, and then all the beams land on the diode at the same time. Again, it's a square law detector, so you get some indifferences. And these three features here will be mapped out to 80 megahertz at the diode. And so we've just implemented this. And again, what we want to do is measure this asymmetry that tells us the temperature of our membrane. As a bonus, you also amplify the signal doing this. So here are some initial results that we took a few weeks ago. Right away you see an asymmetry, but I just want to underline and orally and on this slide that this is not the quantum asymmetry we're looking for. For this set of parameters, the n is about 100, so we're not at the quantum regime yet. Actually, so this asymmetry that you're looking at right here is coming from something totally mundane, which is that we have a sort of asymmetric gain profile in our electronics, and we're just calibrating that out, and there's not much to say about that. However, there are some other interesting technical systematics that this sideband thermometer is hiding in. For example, one thing we've learned about our cavity is that it has different polarization modes, and these modes are split due to birefringence in our mirrors. And then there's also these correlations between laser noise and the membrane motion. And so the rest of my talk is going to just tell you what we're thinking about these 2 points, basically. So the first thing is this thing that we learned about our cavities. The mirrors are birefringent. Maybe the membrane is birefringent too, and they're at some funny angle relative to each other. And so that means that the orthogonal polarization modes are no longer degenerate. There's a set of normal modes, and they're split. In this case, we've measured it by about 380 kilohertz in our system. And what we really want to do is compare our data to a simple theory involving one optical cavity. We basically have 2 optical cavities, and I've labeled the polarizations M. Oh, sorry. Yeah, so we have 2 optical cavities. And so what we really want to do, the first thing that we want to tackle is we don't want to have the cooling beam go down at a slightly different frequency from the measurement beam, land on the diode, and start beating with the measurement beam, because that'll give you a whole lot of signal that you don't want to look at. So what we want to do is reject the cooling beam. And in order to do that well, we really want the cooling beam to address this upper cavity mode, and we want the lock beam to address this lower cavity mode so that we can address the normal modes of the cavity and then reject it much easier at the top. I'm not being very clear about this, but maybe if I step you through it. Basically, we have our laser putting out orthogonal polarizations that I've labeled H and V here for the lock and the cooling beam. And in order to map these linear polarizations onto whatever the normal modes are in the cavity, we have a series of wave plates, and that maps that into the M and the C polarizations. It interacts with the cavity, comes back, the wave plates undo what they did, back to H and V, and then we have a polarizer to reject the cooling beam. So, right. So with this in mind, after we've optimized all of this stuff, we were able to then park the lock beam right here and then step the cooling beam to different frequencies and measure the optomechanics in our system. And what we see when we do that is something close to what we would expect qualitatively. So you see here's the half width of the Brownian motion as a function of detuning, and you see a peak when the cooling beam is the mechanical frequency away from the upper cavity, and then it tails off. And you see an optical spring with this funny shape, and that's just what you expect for resolved sideband optomechanics. Okay, and each of these data points comes from a spectra such as this, and all of our spectra fit very well to a Lorentzian, and in general, actually a Fano line shape, because as we move the cooling beam closer and closer to the sweet spot, the spectra start looking a little bit funny. We have this asymmetric Lorentzian, and then we actually get this inverted dip that a couple of different groups are seeing. And so obviously, when you're doing a heterodyne measurement, you're sensitive to amplitude and phase noise. And so it turns out, due to funny feedback in the system, the area no longer corresponds directly to the Brownian amplitude. And so we have to untangle all of that. So what this is coming from, actually, is correlated noise in the membrane's motion. It's being correlated with the noise on the laser. And the idea is that basically you have noisy light going into the cavity. That causes a correlated noise force on the membrane. The membrane responds with its susceptibility, so it has correlated motion. And then that puts correlated phase noise on the light in the cavity, which then leaks out and interferes with the noise that was coming in the first place. And so your background can get these funny dips in it. And if you just start with this intuition and you just plow through all of the equations, you can predict what you expect to see for our red and our blue mechanical sideband. And it has this form right here. And this theory was worked out by Borgia. Borgia? Okay. I'm really embarrassed to try to pronounce this in front of everybody, but okay. Anyway, he's been very helpful. He puts up with a lot of really dumb questions from me specifically, so I'm ever grateful. Anyway, there's a lot of components here, and I'll just walk you through them. Basically, we have the membrane motion giving you phase modulation, and that appears here, and this is our thermometer signal. And then you have technical and shot noise on the laser. That gives you a roughly flat background at the mechanical frequency. That gives you these two terms. And then you have, from the classical noise on the laser, you have correlated membrane motion driven by the laser noise. And that gives rise to B and C here, which are different for the two sidebands. And so in general, you have a Fano line shape coming from the laser noise and a symmetric Lorentzian coming from this thermometer signal that we're looking for. Okay, so as I mentioned, all of our data has fit very well to this Fano line shape. And so without doing any complicated calibrations to try to untangle stuff, we can do a few sanity checks first. So here I've plotted the symmetric and antisymmetric amplitudes of our line shape. And as you see something that's qualitatively makes some sense. Our symmetric amplitude goes to near zero right when the cooling beam is on the lower sideband. Our antisymmetric component goes near zero at the same place, so that's just saying that we're damping out the motion. That's encouraging. One thing we shouldn't see, however, is a dependence on this antisymmetric component, a dependence on the cooling beam detuning. And the reason for this is that in Hjettel's theory, the antisymmetric component right here should only depend on the classical noise of the measurement beam. So whatever the cooling beam is doing, it should just change the mechanics and not show up in our signal as an antisymmetric Lorentzian. So this right away kind of hints that what we're not doing well is rejecting all of the cooling beam. And it's not surprising, considering the way that we took this data was to park the cooling beam at this frequency, monkey with the rejection optics until it completely killed the beating. And then when we moved it to different detunings, the polarization rotated a little bit and some more of it leaked through. And so that gave us this extra Fano line shape. Okay, so that's one sanity check. We can also compare with the optomechanics theory, so all of the line widths and frequencies of these peaks that we fit. Again, this is the data. And what we've done here is laid the theory curve on top of it. We haven't done a fit here or anything. All we've done is just estimated our parameters independently at the 10 to 20% level. And the agreement is actually quite good, especially for the optical spring. There's a few discrepancies, and most notably, right around this detuning, the theory predicts an optical damping that is much larger than what we're actually observing. And we're not exactly sure what's causing this, although our experiment is not directly matching with Hjettel's theory. He's made some assumptions that simplify the theory substantially. For example, the two beams should have totally uncorrelated noise, and they should be perfectly isolated, and there should be none leaking through to the diode, and these kinds of assumptions. And in our system, we have a laser that's being fed into some modulators, and that makes both of our beams, so the noise is correlated on the two beams. That's one problem. And this rejection, we can't necessarily address this better than 95% or 97%, so there is some copolarized beam that causes beating. And then our rejection is probably not perfect at all frequencies too. So we're just trying to figure out exactly what's causing this discrepancy, but it's encouraging first results. Another funny thing that we've been kicking around in the lab is that this could be arising from this optomechanical electromagnetically induced transparency. The way to understand this, our argument is basically if you imagine the measurement beam, it also is applying some optomechanics. We've worked very hard to put it right at the center of the cavity so that it wouldn't do anything. But nonetheless, if it gets dragged to a different detuning, it will start to apply some damping and anti-damping. And notably, this discrepancy is occurring at the mechanical frequency away from the lower cavity, which makes us think that perhaps this 3 to 5% of the cooling beam that leaks into the lower cavity is doing some funny heating, or perhaps it is beating in the cavity. I mean, we know that will happen, and that can actually this beating intensity can drive the membrane and cause this correlated motion that gives rise to this funny thing where if you put the cooling beam right here, basically you get a notch in the susceptibility of the lower cavity, and this is this EIT thing that people have talked about. And if there's a notch, you could be distorting where the lock point is and adding some extra optomechanics and other confusion. So we think that this notch should be only 100 hertz wide, but it could drag it around. Anyway, this is just one idea. So the take-home message here is that the system we're actually using to do our optomechanics doesn't match the theory that we're trying to fit it to. At this point, we can decide how we want to spend our time. We can ask Yettel to take into account all of these different variables in our experiment, or we can try to make our experiment look a lot more like Yettel's theory. As an experimentalist, we really opted for the latter, and it's also just rude to ask someone to model all of these strange effects. So now I'm just going to show you some of the things that are going on in our lab. The first thing we want to do is, instead of using one laser to generate our beams, use two. And the idea being that the noise in these things will be uncorrelated. That'll match the theory. And as an added bonus, with two lasers, we can do this neat thing where so here's the transmission data again. This is the detuning of the laser and the displacement of the membrane, and these are separated by our free spectral range. And if we apply the measurement beam at one frequency that's addressing this mode, and apply the cooling beam at a frequency that's addressing this mode, that's about 8 gigahertz apart. So any kind of funny beating effects at the diode or inside the cavity are going to be totally irrelevant for us in terms of the mechanics. And so we could even have these beams aligned on the same polarization and really address only one of these optical cavity modes, which has been limiting us. So we've been working on locking our two beams together in the last couple of days. Here's a picture. Here's our two lasers back to back, ready to take on the world. We pick off some of their power and feed them into a photodiode that has a really high bandwidth, and then that lands on a mixer, and we have an 8 gigahertz source that we can use to tune the difference frequency between these lasers. And so we can lock one laser to one cavity mode, and then sweep the cooling beam relative to that and do our optomechanics very detuned. So this is a promising direction to take. The second thing is, if it turns out that our laser is too noisy to get to the ground state, we have filter cavities in our lab, and one of them is shown here. Well, this is the indestructible can that's holding it, but basically there's a cavity inside there that has something like a 20 kilohertz line width, and so the idea would be to just feed the laser into this cavity, and then what comes out should be something close to shot noise limited at 261 kilohertz. How much time do I have?
You have, let's see, about 5 more minutes, 6 more minutes, and we should go to questions.
Awesome. Okay. And so, once we have shot noise limited laser light, we can feed those into AOMs, and we can tune them relative to each other that way. Okay, so that's a cool direction to take as well. And on the analysis side, we can start to understand our data a little bit further. Up until this point, I've just been showing you PSDs where we treat the sidebands sort of independently. We're throwing away the phase information, and Yettel has predicted that there's some information in that phase. And so there's this third quantity that we're starting to look at now, called the cross correlation of the sidebands. Basically, you just take the FFT of the lower sideband, fold it on top of the FFT of the upper sideband, multiply them, and then you get something that also looks something like a symmetric and an anti-symmetric Lorentzian with different coefficients, and you can pull out more information from this. And this is very, we've just started to look at this. We've been focusing on the experimental side up until this point. So anyway, these are promising directions to take. So with that, I'll summarize. The things I want you to remember are we've been making some technical advances towards ground state cooling. I showed you that we've gotten down to the 10 to the 20 phonon level, and we've implemented a heterodyne measurement, and we're hoping to do sideband thermometry. But the sideband is actually hidden in some technical noise, and we're kind of untangling that. And so that's currently an open discussion. And our current main push is to just simplify our system by adding another laser and a filter cavity. And the main point I want to make is that these challenges do not seem fundamental. They're very technical in nature, and so it's just a matter of time. Okay, so with that, I'd like to thank my collaborators, Jack Harris, my PI. He's brilliant and also a very nice guy. So if you're looking for a postdoc or a grad career, just call him, look him up. And Andrew J.H. has been working very closely with me on the refrigerator system. It took 2 years to work, and that's a real testament to his technical skills in the lab. These three guys here basically taught me everything I know about optomechanics when I joined the lab, forever in their debt. Andre retrofitted our lasers so that we could perform this mechanical ring down at low temperature. And of course, Kjetil has been instrumental in telling us what we're actually seeing in our data. So thank you.